Okay, so having talked about the construction of the set of reals briefly, namely that the reals form an ordered field satisfying the least upper bound property with the rationals as a subfield, we are going to conclude this chapter by talking about two supplementary topics related to the set of reals. Specifically, in this video, we are going to talk about the extended real system. Now, what is the extended real system? The extended real system is a set that consists of all the elements of the reals R and two elements plus infinity and minus infinity. Okay, so these are currently just two symbols. They are not numbers, of course. So we introduce two symbols plus infinity and minus infinity and define certain rules associated with how elements of R interact vis-a-vis ordering, addition, multiplication with these symbols plus infinity and minus infinity. Okay, and this union of all the elements of R plus infinity and minus infinity is what we call the extended real number system. Okay, so the ordering within R is of course already well defined. So far as ordering is concerned, I first have to tell you how plus infinity and minus infinity are ordered relative to the other elements of R. So we preserve the natural ordering in R. And we define the ordering itself as follows. So for all x in R. Okay, so this is how I define ordering by including these new symbols plus infinity and minus infinity. So the ordering is that every real number x is greater than minus infinity and less than plus infinity. Okay, it's just a definition. So when I'm extending R by introducing these two symbols plus infinity and minus infinity, here is how the ordering extends. Okay, similarly we will also extend multiplication and addition. Okay, so we use the following conventions. Relating to addition and multiplication. Okay, so first I'm going to tell you how things work with respect to addition. If x belongs to R, we say that x plus infinity, which is the same as x plus infinity, is equal to plus infinity. Similarly, x minus infinity by definition is going to be minus infinity. Yeah, so that's with respect to addition and subtraction. And with respect to multiplication and division, let me first talk about division first. If x belongs to R, x by plus infinity equals x by minus infinity is equal to 0. And now if finally with respect to multiplication, if x is greater than 0, then x into plus infinity equals plus infinity, x into minus infinity equals minus infinity. Okay, on the other hand, if x is less than 0, this is reversed. If x is less than 0, x into plus infinity will be minus infinity, x into minus infinity will be plus infinity. Okay, so these are the conventions when it comes to addition, multiplication, subtraction, division extended to the extended reals, namely including the symbols plus and minus infinity. Okay, So I've told you how ordering works in the extended real system, and I've talked about how addition, subtraction, multiplication, division works in the extended reals. Okay, so one thing to note is that R union plus infinity minus infinity. Now this set is exactly what we call the extended reals. Okay, symbols plus infinity and minus infinity appended to R, if you will. This is not an ordered field, not even a field in fact. Okay, so think about this a little bit. You'll find any number. So if you look at the rules when it comes to addition and multiplication that we have laid out above, you will find numerous instances where we are deviating from the rules of a field. So while R itself is a field, in fact it's an ordered field, the set of extended reals, which includes plus infinity and minus infinity, is in fact not a field. Okay, so go back and convince yourself of why that is the case. You should be able to find several examples. Let me maybe lay down one. If it were a field, then you would have that 1 plus infinity is equal to 2 plus infinity, because after all both of these are infinity. By the cancellation law, that would imply that 1 is equal to 2, right? Which is of course not true. Right, so that's just one counter example of why the set of extended reals is not a field. You should be able to find violations of other axioms and the rules I have laid out above as well. Okay, so now that I have introduced the extended reals, I want to do one simple proof which kind of firms up the concepts that we have laid down. But before I do that, let me talk about how I can deal with infimum and supremum when it comes to unbounded sets. Okay, so yeah, let me make that another note. So let S be some subset of R. Okay, now if S is bounded from above, we know from the fact that R satisfies the LUB property that the supremum of S exists, is in fact an element of R exists. Okay. On the other hand, if S is not bounded from above, we define supremum of S as plus infinity. Okay, so we've already talked about how if you have bounded sets that are bounded from above, then their supremum exists, and what I mean by that is that the supremum and the least upper bound is in fact an element of R. If it is not bounded from above, then I just define the supremum to be plus infinity. Okay, one small side note for you is that we typically write plus infinity as infinity. Yeah, so I probably won't carry the plus forward, in the remaining material. So this is the first thing, right? So by this notation, essentially, the supremum is well defined for all subsets of R, right? The supremum for subsets of R that are bounded from above is an element of R. If the set S is not bounded from above, we just define the supremum to be plus infinity. Similarly, for sets S in R not bounded from below, we define the infimum to be minus infinity. Okay, so put all of these together and you realize that within the set of extended reals, supremum and infimum, are defined for all subsets. Right? For suitably bounded sets, upper bounded sets in the case of supremum and lower bounded sets for the case of infimum, the sup and inf are in fact elements of R. Otherwise, the sup is plus infinity, the inf is minus infinity. So within, so long as the sup and inf are taking values within the extended reals, they are well defined for all subsets of R. Okay, so this is a matter of convention that we should keep in mind. Using this convention, we are now going to prove one theorem. So suppose that A and B are subsets of R, where A and B are not empty. Okay, in that case, the following is true. Supremum of this set A plus B, if you don't know what that is, I'll define that in just a bit. The supremum of the set A plus B is supremum A plus supremum B. Infimum A plus B is equal to infimum A plus infimum B. Now, in case you haven't encountered set addition before, let me define that formally here. So A and B are of course non-empty subsets of R, as the hypothesis tells you. The set A plus B is defined as follows. It's the set of all elements which are sums of elements in A and B. So A plus B is the set made up of elements of the form A plus B, such that A belongs to A, B belongs to B. Okay, so you construct this set which we call capital A plus capital B, the set summation if you will, as basically consisting of all elements that can be obtained by adding together elements of A and B. Okay, so this is the definition of set addition, and based on this definition of set addition, what the theorem says is that if the sup of A plus B, the set A plus B, is in fact the sup of A plus the sup of B, similarly the infimum of A plus B is equal to infimum of A plus infimum of B. Okay, and of course all of this is within the generalized definition of sup and inf that we have just laid out. Namely that sup and inf are now well defined for all subsets of R, right? Except that the sup may be plus infinity, the inf may be minus infinity, right? And if one of these is plus infinity or minus infinity, then the sum of say sup A and sup B, or inf A and inf B, would be interpreted based on the rules of addition subtraction involving the infinities that we have just defined. Okay, so now let us get into the proof. Okay, so now I'm just going to prove one of these statements. So let's say I'm going to call this statement 1 and statement 2. So we are going to prove 1 and 2 is an exercise. Okay, now this proof, I'm going to do this in two steps or two cases. Okay, so let's look at case 1. This is in fact the trivial case. The trivial case is that the right hand side of the equation 1 is infinity. So case 1 is that sup A plus sup B equals infinity. Now, what does it mean for this to be true? Now, the only way that sup A plus sup B is equal to infinity is if one of sup A or sup B is infinity, right? So this means that either or both of A and B are unbounded from above. Okay, So the only way soup A plus soup B can be infinity is if one of soup A or soup B is infinity, which implies that at least one of the sets A and B should be unbounded from above. Now, if one of these two, one or both of the sets A and B is unbounded from above, it's not difficult for you to see. Again, I am going to ask you to convince yourself of this, that the set A plus B is also unbounded from above. Right? And if A plus B is unbounded from above, by definition, soup A plus B equals infinity. Right? And that completes, in fact, the proof of case 1. So the easy case is handled, somewhat trivially, namely that if soup A plus soup B is infinity, then clearly soup of A plus B will in fact be soup A plus soup B. Okay. So now let me move on to the more general case, or not the more general case, but certainly the more non-trivial case. So case 2 is that both soup of A and soup of B belong to R. Okay, so now I need to show that in fact soup A plus B is in fact still equal to soup A plus soup B, both of which are, well, real numbers. Okay, so the way we are going to go about proving this is to show that soup A plus B is greater than or equal to soup A plus soup B, and that soup A plus B is less than equal to soup A plus soup B. And since both of these are true, it could only possibly be that soup A plus B is in fact equal to soup A plus soup B. Okay, so let's begin in this manner. For x belonging to the set A plus B, we have x is equal to A plus B, where A belongs to the set capital A, B belongs to the set capital B, right? By definition, every element of the set A plus B is expressible as a sum of elements of capital A and capital B. Okay, so since x can be expressed in this manner, it follows that x is less than or equal to soup A plus soup B. Why? Because by definition, soup A is an upper bound on the elements of set A. So therefore, the element small a is guaranteed to be upper bounded by soup A. The element small b is guaranteed to be upper bounded by soup B. So therefore, any element x of A plus B is upper bounded by soup A plus soup B. Right? So in words, what this means is that soup A plus soup B is an upper bound. On the set A plus B. Now, since soup A plus soup B is an upper bound, clearly it is going to be greater than or equal to the least upper bound. So therefore, soup A plus B is less than or equal to soup A plus soup B. Okay, let's call this star. Okay, so because soup A plus soup B is an upper bound, soup of A plus B, which is the least upper bound, must be less than or equal to soup A plus soup B. Okay, so that's one side of the inequality. Now let's try and prove the other. Suppose we are given any epsilon greater than 0. Okay, then it follows that there exists elements A tilde in A, B tilde in B, such that A tilde is going to be greater than or equal to soup of A minus epsilon by 2. Similarly, B tilde is greater than or equal to soup B minus epsilon by 2. Now, why is this true? This is actually true because of the fact that, soup A is in fact the least upper bound of the set A. Therefore, soup A minus epsilon by 2 is in fact not an upper bound on A. So what does it mean to say that sup A minus epsilon by 2 is not an upper bound on A? I should be able to find at least one element in A. I'm going to call it A tilde, which is greater than or equal to sup A minus epsilon by 2. Right? And an analogous argument applies to sup B minus epsilon by 2 not being an upper bound of the set B. Okay? Now, therefore, A tilde plus B tilde is going to be greater than or equal to sup A plus sup B minus epsilon. Okay? Now sup of, but remember this fellow belongs to the set A plus B. Right? So from here we can conclude that since I have an element of the set A tilde plus B tilde is in fact an element of the set A plus B, it should in fact be bounded from above by the sup. Right? So sup of A plus B is in fact greater than or equal to A tilde plus B tilde. Right? By definition, because sup A plus B is an upper bound on the set. That in turn is further greater than or equal to sup A plus sup B minus epsilon. Right? So that almost gets us to the end of the proof. From this we conclude that sup A plus B is in fact greater than or equal to sup A plus sup B minus epsilon. Now, in particular, this statement is true for every positive epsilon. Okay, so since epsilon greater than 0 is arbitrary, it follows that sup A plus B is greater than or equal to sup A plus sup B. Okay, again, if you have not seen this type of argument before, think this through. Namely, the fact that this statement here holds for every positive epsilon in fact implies that it also holds if you put epsilon equals 0. Okay, so convince yourself of this. Since so far as this argument is concerned, the value of sup A plus B, sup A and sup B are irrelevant. All you really have is that some number is greater than or equal to another number minus epsilon for all positive epsilon. Right? That in turn implies that some number is greater than or equal to other number. That's really all that we are saying here. And I want to emphasize that there is no limit here. We haven't talked about limits yet. So I'm not taking epsilon to 0 because I haven't defined what it means to say that the limit epsilon goes to 0 in the context of this course yet. Right? We're going to get to limits in the next chapter. I want to emphasize here that this implication does not have anything to do with limits. It is just an elementary consequence, if you will, of the ordering on the reals. Okay, so now that this is now your statement, let's say star star, and if you combine star and star star, that implies in fact that sup A plus B must be equal to sup A plus sup B. Right, and that brings us to the end of this proof.